Welcome to the acid-base properties of salts. So, recall that all acids have a conjugate base, and all bases have a conjugate acid. So the strength of our conjugate acid or base is inversely related to the strength of the acid or base. So, if we have something like hydrochloric acid, HCl, it's a strong acid, and sodium hydroxide is a strong base. So chloride is our conjugate base of our hydrochloric acid, but it's got a negligible tendency to accept a proton. That means if we put chloride ions in solution and we put some protons in solution, they're not going to combine. If we have sodium ions, sodium ion is the conjugate acid of our sodium hydroxide, which is a strong base, but the sodium ion has a negligible tendency to donate a proton or cause water to donate a proton by reacting with hydroxide. And this means that the conjugate base or acid of a strong acid or base has no effect on the pH, which means it's a negligible acid or base. So if we have something like a salt containing these two, so sodium ion is the conjugate acid of a strong base, which means it has a negligible acidity. Chloride is the conjugate base of a strong acid, which means it has negligible basicity. Which means if we put these two into solution, we're not going to change the pH. We can put as much sodium chloride in there as we want, and as long as we have no other acids or bases around, we're not going to change the pH. But if we have something like sodium acetate is the conjugate base of a weak acid, acetic acid. Now it's not the sodium part, it's the acetate part here that is the conjugate base of our weak acid. So an aqueous solution of sodium acetate has sodium ions and acetate ions and water as our major species. But remember, sodium ions have no effect on the pH, but acetate can react with water to form hydroxide. So if we have acetate ions plus water, we get acetic acid and hydroxide ions. So we can then define our equilibrium constant for this reaction, our base dissociation constant, as Kb is equal to the product concentrations, the acetic acid times hydroxide ion, divided by the reactant concentrations, our acetate ion. Again, we've left off the water here because it's a pure liquid. And we know that Ka for acetic acid is 1.8 times 10 to the minus 5. But we don't know what Kb is, because Kb is not the same thing as Ka. They're related, but they're not the same thing. Because this is the base dissociation constant, whereas this is the acid dissociation constant. So, remember that Ka is equal to the hydrogen ion concentration times the acetate ion concentration divided by the acetic acid concentration. Right? H plus concentration times A minus concentration divided by HA is equal to RKa. So, let's multiply Ka and Kb together. So we have Ka times Kb, we have our Ka here, and we're going to multiply that by our Kb fraction here. Well, you notice that here we have an acetate, and that's going to cancel with this acetate. And here we have a acetic acid, and that's going to cancel with the acetic acid there. And now we have nothing in our denominator, and in our numerator we have hydrogen ion and hydroxide ion. Hydrogen ion concentration times hydroxide ion concentration, that's Kw. Which means that for any acid, Ka times Kb is equal to Kw. So, now we have a way of relating Ka for some acid to the Kb for its conjugate base, using the autoionization constant of water. So, for any of our conjugate acid-base pairs, we can say that this reaction is true. And now we can calculate either Ka or Kb from the other one. Furthermore, we know that because the product of these two has to be equal, the larger Ka gets, that means the stronger the acid, the smaller Kb gets, the weaker the conjugate base. So, if we have a really strong acid, then our conjugate base has to be really weak. If we have a really weak acid, then our conjugate base has to be a really strong base. So, another way of looking at this is that because acetic acid only partially dissociates, then that reverse reaction occurs to a significant extent. If we have a lot of our acetic acid in this form, then because some of it is dissociated, some of it must be reassociated and getting reformed. So, the further to the right this equilibrium lies, the stronger the acid is, and the weaker our conjugate base gets. Because if more of our acetic acid is dissociating and less of it is getting reassociated, then less of our acetate is reacting with a hydrogen ion, and that means that acetate is a weaker acid. The less that happens means that's a weaker, acetate is a weak base, right? That's a weaker base. So, this was the acid-base properties of salts.